Python tutorial given by Kurt Smith. So Kurt is a software developer, scientific software developer at Enthought, and also a very regular and experienced trainer. And he has a PhD in plasma physics from the University of Wisconsin. And he's also somebody who knows Cython extremely well for contributing to it. And so he's going to show you some of the old things that have been in there and that are really powerful, and some of the new things as well. So I'll leave him the floor.
Thank you, Jonathan. Thank you, everyone, for being here. And I really appreciate everyone going through the possible pain of verifying that Cython will work on your system before this tutorial. I really appreciate it. I'm encouraged by the relative lack of support emails that I got, that I think everyone's in pretty much good shape, and I was able to get almost everyone in working shape, except for maybe one or two that I wasn't able to get to. So at the exercises, I can certainly sit down with you, and hopefully there won't be too many who have a system that needs some TLC to get in shape here. So really make things go smoothly today. So as Jonathan said, I've contributed to Cython, and I did it because it was a project that was just fantastic. Really like it. The idea of it is great. Just taking Python code, allowing you to optionally add type information and speed it up. I used it extensively for my graduate work. I did high-performance, massively parallel turbulence simulations of astrophysical plasmas. And the core code was all in NumPy and Fortran. And everything before that was Python and Cython, and everything after that was Python and Cython. So on the front end was all Python, really, and then the back end, all the data processing, all the everything else was Python and Cython for speeding things up. So I found it to be a fantastic combination for doing science, and I'm extremely encouraged by the activity that's going on in improving the tool set for doing scientific computing in Python. Cython is, as you'll see here, it's becoming more and more part of the infrastructure of doing scientific computing in Python, and we'll see why that is, hopefully by the end of the day today. All right, so let's get started here. So I should mention I'm fully aware that I can run in presentation mode in PowerPoint, except when I do and I flip back and forth between PowerPoint and anything else, by about the 5th time it crashes on me. So I just leave it in presentation mode, and I hope it's large enough for everyone here. So that's what I'm going to stick with. So to get to the core of what we're doing today, on the left we have a simple Python function computing the Fibonacci sequence. Okay, and it's using some nice Python goodies like multiple assignment, a comma b equals 1 comma 1. For I in range n, we do a comma b equals a plus b comma a. If you haven't seen this before, it's one of Python's great ways of doing many things on one line in a very expressive way. So I'm going to take this function, and I'm going to put it into an IPython notebook. Apologies. All right, so here's my fib function. And fib of 10 gives me, let's just do fib of 3 just to keep it simple. We get 5 back. Now, the point of Cython is to take something that starts out as Python, so you'll be able to be very expressive with it, and add optional type information to it, okay? And eventually get down to something that looks like this C or C++, or at least conceptually is equivalent to the C or C++ on the right here, okay? So on the right, we have the equivalent C or C++, and then down here is how you would conceptually merge the two. You take the Python on the left, the C or C++ on the right, and you add the type information from the C to the Python syntax on the left, and you get this. You're able to stick an int in the argument signature, so it looks like a C integer now. And even though this isn't valid Python anymore, it is valid Cython. And you and I know exactly what is intended here, even though the Python interpreter doesn't, right? This line here is essentially a C declaration, where we say cdef int I, A, and B. So we're declaring I, A, and B as ints. The cdef is just Cython, new Cython keyword, but you can essentially ignore it. It's just helping the Cython parser figure out what you're declaring. But that's all you have to do. And Cython's able to take that code and generate essentially this C and C++ code on the right here. Okay, so that's the core of what's going on. Now you may be wondering about runtime. And if the Python version runs at 1 unit of time, then the C and C++ version is going to be 70 times faster. And the Cython version is also going to be 70 times faster if you run this. Okay, so we're getting the exact same performance out of the Cython code that we would expect out of the C and C++ version as well. Now you may be wondering, what if I were to do this all in hand? What if I were to take a C extension, create my own C extension module in C, and use all the headache and pain of Python's distutils and get all the right compiler flags right and have to worry about all the details of the Python C API to get everything working right? This is what you'd have to do for that simple Fibonacci function. Now, granted, this isn't that much code. This is a complete C extension module, and it will work if you take this and stick it into a C file and compile it properly. But it's still a lot of stuff there, and you have to know all the details about how to use pyargparse tuples correctly, how to use pybuildValue right, how to create your own PyMethodDef table, how to call pyinit module right, those sorts of things. So Cython's taking care of all this for you. And the really surprising thing is that this handwritten C extension module is only 40 times faster, not 70 times faster like we saw with the Cython version here. Okay, you may be wondering, well, why in the world is Cython faster than a handwritten C extension module? And the answer is because Cython's generating some heavily optimized C code. For instance, Cython doesn't even call pyargparse tuple. It creates its own, it does essentially the same work as pyargparse tuple, but in a much faster way. That's just one example. So when you're using Cython, you may be thinking, well, I'm making a compromise between Python and C, but in fact, you often get code that's faster than if you were to write it by hand. Okay, and so that's one thing. It's not just you don't have to feel like you're compromising in performance. You're actually getting better code than you may be able to write yourself. Okay, so that gives you just a taste of what's going to happen here today, as far as the ability to take Python, speed it up by adding type information. Let's talk about what exactly Cython is in more formal sense. So I like to think of Cython as a Python-like language that is designed to improve Python's performance by adding type information. And it's not uncommon to get 3 orders of magnitude or more speed up, okay, especially for numeric programming. And it's not necessarily that Cython is that good, it's just that Python is that slow at numeric programming, okay? And so all you're doing is you're just tapping into the performance of native types that are able to fit inside of a single register, rather than having boxed types that Python provides, like boxed integers or boxed floats or boxed complex values, for example. So Python's got a lot of stuff around all the core data that's representing that integer or that float or that complex value. Cython does away with all that, and you get much better performance as a result. You can wrap external code with Cython. That's the other main usage. And you can wrap C, C++, Fortran, anything else where you know the ABI for that language, the application binary interface, you know the name of the symbol that's in that object file, you can wrap that with Cython. Okay? And these are the 2 ways that Cython is most commonly used: for wrapping external libraries and giving you a lot of control, a lot of power to be able to give a very custom, very nice Python interface, and speeding up existing Python code. Okay? We'll be going over both of those today. There's a Cython command that comes with the Cython source package, all lowercase Cython. And that command, its job is to generate an optimized C or C++ source file from a Cython PYX file. Okay, so all Cython does is the source-to-source translation tool. It takes Cython source and it generates C or C++ source for you. Then it's up to you to roll that generated extension module into your infrastructure. Okay. Thankfully, there's several other tools that make this even easier. So we don't always have to worry about getting compiler arguments just right, that sort of thing. Okay. And we'll see plenty of those later on today. And as I mentioned here, the C or C++ source is then compiled into a Python extension module. And so Cython, it just does one thing, but does it really well. And it's up to you as far as how you want to use the results of what Cython does for you. So some other big features that are good to point out about Cython. It has built-in support for NumPy. There's a lot of numeric users of Cython. And so they paid a lot of attention to it, and so Cython has first-class support for working with NumPy arrays. It integrates with IPython. We'll see that in just a few slides here. And the whole idea of Cython, the whole name of Cython, is combining C with Python. Okay? So, and it does it in a very fluid, very flexible way. All right, so how are people using Cython? Well, question, yes? We'll see in a little bit that there's nothing automatic about Cython's wrapping. You have to do everything by hand, although there are separate packages coming out, I'll mention at the end today, that takes care of some of that automation for you. Okay, but yeah, there's nothing automatic about it. Is there another question? Yeah, here. Good question. So again, it all depends on what you're wrapping, but as Cython, so Swig by design will generate a compiled extension module and a .py file. And when you call the wrapper in Swig, you're calling through that Python file, and then that calls into your extension module. So there's an extra layer of Python between the compiled code in Swig and your code that's calling it. So by design, there's an extra layer there. That may or may not make a big difference for what you're doing, but it's generally Cython, if you just look at just the wrapping layer, Cython is generally faster than Swig. So for simple stuff, they're going to be almost identical in performance. For more complicated things, Cython will usually win out by a measurable margin. Okay. All right, so just spent half an hour this morning looking at some of the fundamental packages for scientific computing in Python. I don't have to explain any of these packages here. You all know what they are. And just looking at how much Cython they use. And so we have NumPy, SciPy, Pandas, SymPy, scikit-learn, scikit-image, Sage, and MPI for Pi. We just tallied up the number of Cython files, and that includes PYX files, PYD files, and PXI files. And then the total number of lines of code in thousands, okay? So NumPy, I was surprised to see that NumPy had any Cython code, since it's, to my mind, it's kind of a bootstrapping problem, but you have Cython that uses NumPy heavily, but NumPy is using Cython to some degree. So, but anyway, it's there. I was really surprised to see a little bit, so 5,000 lines or so. SciPy uses it more, about 18,000 lines. Pandas uses it heavily for a lot of its optimization. Pandas uses underneath the covers something called, I think it's called bottleneck or fast bottleneck, something like that, and it uses Cython heavily as well to speed up NumPy. SymPy uses it tremendously. The one that I should really mention here is Sage. Sage is a driver of tons of Python development. Sage. Robert Bradshaw was at University of Washington. He worked with Dr. Stein on the Sage project, and a lot of Robert's work was taking the lead on the Cython project. He's still the lead there. And so Sage drives a ton of Cython development, and you can see here it uses a tremendous amount of Cython for what it does. So definitely Cython would not exist today without the support in the background, the support and the development time devoted to it from Sage. Lastly, NPI for Pi, if anyone's doing parallel programming, it wraps the NPI library using Cython. So if you're not using Cython directly, you're using it indirectly, given that it's becoming part of the infrastructure of doing scientific computing in Python. Okay. Before I continue, what time is our break so I can make sure I time things? 10:30? Sorry. 3, okay, thanks. Before 3, okay. Okay, that's a strong incentive, all right. So if I don't stop by 3, you guys are just gonna get up and go anyway, so, okay. Before 3, all right. It's going at 3:30, yeah, okay. Okay, thanks. All right, so again, the 2 modes of using Cython, one, speeding up Python. So we have our fib function, we add our type information there with Cython, that's your job. You add the int information there, the cdef compilation line. You call the Cython tool either indirectly or directly, and it spits out this generated C code for you. Okay? I'm not going to show you the generated C code. It's quite ugly, a lot of mangled stuff in there, but you can make sense of it if you need to. And it actually, I learned a bit about optimizing C code from looking at how they optimize the C code generated by Cython. The other direction, you have existing compiled code, C++ code. Here we have a little function called fact, and just recursively calls fact again to compute the factorial. Very simple little function. It's nice, I can fit it on one slide here. And then we have Cython code that's designed to wrap this simple little function fact. Okay? And we'll go through all this in more detail later. And here's just 4 lines of Cython code. We just tell Cython what the interface for this C function is, and then we create a Python function that will wrap it. And then Cython, again, spits out a generated extension module, and we compile that, and it compiled along with our C code, and we have now our extension module that's wrapping our factorial function. Okay? So those are the 2 main modes of working with Cython, the 2 objectives. And there's this new mode that's come along fairly recently, last couple of years, that you can use Cython very interactively via IPython. Okay? And there's a Cython magic %% Cython, and we'll see how to use that here. So if you don't already have an IPython notebook up and running, I urge you to do so now. Let me bump up the size here. So in order to use Cython in IPython dynamically, first thing you need to do is tell IPython that you need to pull in the Cython magic. So what you do that is by %load_ext Cython magic, like so. Okay. And if your system's able to run that line, you're halfway there. If it isn't, it means you have an old version of either IPython or Cython, and things aren't working. So you need to update either or both of those. And then now what that does is it provides several Cython magic commands. The one we're going to focus on today is the %% Cython magic. And if you stick %% Cython inside of a IPython notebook cell, the code now, IPython will treat this code as Cython code. Okay, you're no longer in Python code, you're in Cython code. So we can now say def fib int n, and I can do cdef int a b I, a comma b equals 1 comma 1, and for I in range n, A comma B equals A plus B, A, return A. Okay. Now, the moment of truth is when you evaluate this cell. It'll take a little bit, but if it works, you will now have a compiled, what's going on is IPython will take this code, we'll stick it into a source file somewhere, compile it into an extension module, load that extension module, and load in the, essentially do from extension module import fib for you. So now we can say fib, and we get this function. This is the name of that module that it just created, .fib. Okay, so Cython's doing a lot. Sorry, IPython's doing a lot here for us. And the really great thing is that we just care about the Cython code. We don't have to care about the compilation side of this whole thing. So it has this very dynamic feel to it, which is just fantastic for interactive use of Cython and trying things out. Okay. Of course, we can call it fib of 3, for example. So I realized after I wrote my slides up that I use ints for everything here. And Fibonacci sequence grows really quickly, so you quickly run out of room. So don't expect this to be a very good implementation of the Fibonacci sequence. But it's there. As far as the idea of it all, it works, right? We could make these longs instead of ints to have a little bit more room to play with here. Okay.
Is there a quick way to check what the performance is?
Good question. So let's try it out. Let's do time it fib of 3. Like so. It'll churn a little bit. And it gives us 67 nanoseconds, 68 nanoseconds per call. Okay. Let's create a Python version of this. Pyfib n a comma b equals 1 comma 1. Oops. A comma b equals 1. Oops. Plus b comma a. Okay. So there's my pyfib. I hope you agree. It's the identical code to the Cython version minus the typing information. Right. So we'll run that, and then we'll do time it pyfib of 3. Okay, that'll churn a bit. And 8, 10 nanoseconds. So more than an order of magnitude speed up. Okay. Now, this is very much a micro performance measure, but as we saw before, the code Cython generates is heavily optimized, and this makes a big difference, especially for the wrapper layer, when just getting your Python code to just get to the underlying C code, there's a lot of Python between there. There's a lot of calls to parse tuple. There's a lot of checking of argument types, that sort of thing. Cython's done a lot of work to make that as fast as possible while still being correct. And so that's often where the payoff comes, especially when you're calling functions that are mostly just function call overhead and not too much work in the body. So. You can do C++ as well. We'll see that. Yep, you can do template. We'll see that later on. Yep.
Is there a way to search replace in IPython notebook?
That's another tutorial. I don't know enough to be able to tell you. So. Yeah, I wish I could tell you. I don't know enough to be able to say. I'm a Vim guy, so until IPython has Vim inside of the cells, I'm not going to use it that much. So. All right, let's continue here. So I should mention that if you, for whatever reason, you aren't able to use the IPython notebook, or you just prefer the Qt console, for example, or just the terminal version of IPython, this will all work in the terminal version as well. You can do %loadext, Cython magic, and then %% Cython gives you access to the same Cython magic there. Okay, so this is a lower level IPython thing. And I'm just showing it to you in the IPython notebook. It's just one way of accessing it, okay? Okay, so that's IPython. So again, I'm just showing you different ways of working with Cython and the different ways it's intended to be used, okay?
So, quick question. How much of this would be hardware dependent, whatever the performance?
It will be to some extent. I mean, you are getting down to the C level of code. But for that matter, I mean, your Python is going to be somewhat hardware dependent as well.
The reason I asked is because I'm trying to do that on the Bakari thing on the earlier class on IPython, and the time difference I saw isn't much. Like Cython is like 14.1 microsecond, and with just the Python it's 16 microsecond.
Oh, so they're almost the same then.
Yeah.
I see. Yeah, for that, I wouldn't be able to provide much guidance. I'm not sure. I'd have to go into more detail to figure out why that is the case. Okay, so just a flow diagram to just help understand the process for working with Cython source files. So the extension for Cython source files is conventionally pyx, and that's a holdover from when Cython was, Cython started out as a project called Pyrex, started by Greg Ewing, and Cython forked Pyrex, but it's the friendliest fork in the world, where Greg helps out the Cython guys, and Cython guys help Greg out as well. So the reason for the fork is that Cython wanted to be more general and be more aggressive in optimization, whereas Greg was more focused on just wanted very specific things in Pyrex and wasn't willing to accept some of the more edgy features that Cython has. So, but Cython kept the pyx extension. And so you put your code typically in a pyx file, your Cython code in a pyx file, and you call the Cython command either directly or indirectly, and it spits out a C extension file, okay? Here, if it's the Cython source code is fib.pyx, it'll spit out fib.c. And then, again, it's up to you or some other tool for you to compile that C extension module into a Python extension module. And on Mac or Linux, it'll be called fib.so, and on Windows, it'll be called fib.pyd, okay? And if you happen to be wrapping code, like we saw earlier, you would compile, along with that fib.c, any c.c files that you want to wrap, okay? So it's all going to be contained inside of that extension module, and then you can just load that into Python as if it were a regular Python module and go on your merry way, okay? So let's go into that in a little bit more detail. So at the top we have fib.pyx. We just stick our Fibonacci function in there. We've seen that enough times now. And then at the bottom here we have setupfib.py. And for those of you who haven't seen Python distutils setup files, this is a very common pattern that you'll see. You import multiple things. I never remember what these are. I just pull someone else's from the web somewhere and modify it. The core of this is you just pull in what you need, and then you create an extension object with capital E extension. And you give it the extension's name, here fib, and then you give it a list of sources. And you include in there any pyx files that you need to use, and also any .c files or .cpp files for C++ if you need to. Distutils will take all those source files and compile them into an extension module for you, okay? And the way you fire that off is by calling the setup function using this syntax. You give it the extension modules. You can have more than one extension module here, which is why you give a list of extension modules. And this command class is just tying in Cython's ability to run the Cython command automatically for you. So that's all that's going on there. So this is kind of boilerplate that you use for using Python's distutils to compile Cython source code for you. So let's see that in action here. So I should mention that if you should have unzipped that directory, and you'll have, I believe it's named SciPy2013 Cython tutorial. you should be seeing about the same thing that I have here, perhaps not the untitled IPNB. That's the one I just created recently. So let's go into demo and fib. There's a lot of stuff here. Here's our setup.py file. And here's the same code that we just saw on the slide. Okay? So we have our extension object, and then we're calling setup with that extension module. Okay? Yep.
In Cython.distutils, there's also an extension.
Yeah, that's a newer feature. I've not used it much. This way will work. This is the older way of doing it. That's got a little bit more sugar for automating things, so you don't have to pull in as much boilerplate to make that work. But what I'm showing you here is just kind of the older way, which will certainly be around for a long time. But you can look in the online documentation for the newer way of doing this sort of thing. Okay, so that's our extension module. We want to, now what we're going to do is going to tell Python to build this extension module for us from the command line. Okay. So the way you do that is by, let me make sure I have the right Python loaded. Okay. So I'm going to say Python, the name of that distutils driver script, setup.py, and then you say build ext. And then lastly, -- in place. Okay, so that's my line on Mac or Linux. On Windows, you're going to give one more argument, -- compiler equals min GW32. Okay, that last option there is only for Windows. You do not put that. You do not use that on Mac or Linux. So here's Mac and Linux. And again, for those of you who haven't used distutils before, just briefly, what's going on here is we're calling Python with this script. The buildx is an argument to the setup.py script. We're telling distutils what to do. We want you to build an extension, okay? And the -- in place is saying, distutils, stick the result of this operation in this current directory. Don't stick it in some deeply nested build directory somewhere. I want to use it right away, so give it back to me when I'm done. So you run that. Yeah, go ahead.
Can I set the compiler flag on the Cython magic?
I don't know enough about the Cython magic to be able to say. I think I looked into that briefly, and I don't think you can. Although I'd have to play around with it to make sure. Does anyone here know the answer? Can you set the compiler directly on this Cython magic command? I apologize for not knowing this. So I just don't use Windows enough to need it. I presume you got an error when you try to use the Cython magic on Windows. Is that right? No. Okay. Yeah, I apologize. I'll look into that at the break, actually, and get back to you. So from the command line, when we run this, you'll see a bunch of output. The one that's of interest, here, let me get rid of some things here first. Build fib.c. So I need to get rid of the build products first to force it to actually do what I'm expecting it to do. There we go. So here it tells us that it's Cythoning fib.pyx to fib.c. So there that's calling Cython underneath the covers for us to generate our extension module. And then Python's distutils kicks in and takes that fib.c, compiles it. That's what this line is here, this GCC call right here, into a .o file, and then it takes that object file and creates an extension module, fib.so, for me to use. Yep, question? Yeah, sure. So it's the same as this, Python setup.py, build _ ext, -- in place, and then -- compiler equals min GW32. Okay. Question? Well, So let me leave this up here just a little bit. This fib.so, that's the whole goal of this, is to give us this extension module. The in-place tells distutils, put that extension module in this directory. Don't stick it inside of your build directory where you would otherwise. Okay.
That assumes that you've got an ND
That's correct. Yeah, and that was part of the setup earlier. So if you have Anaconda, this should work. I've tested it. If you have nthought Canopy, it should work as well if you've installed the libpython and the mingw packages. Question?
Yeah, I've been around with the command tab and the setup file.
Mm-hmm.
Realized that instead of cdef, I could have put just any functions into the tasks.
That's correct. That's all very specific as far as how it's tying together what commands you're allowed to give to distutils. That's right. Okay, so if that's successful on Mac and Linux, you should see a fib.so as a result of this command, and on Windows, you should see a fib.pyd as a result. Okay. So fire up Python and import fib. We say fib. Now it tells us it's module fib from fib.so, so it is indeed loading this extension module for us to use. And I can say fib.fib, and this is of course our function. I didn't put a doc string in there, but it tells us it's a built-in function or method. And you'll see that if you do len question mark, for example, or I don't know, if you do string dot stir dot, I'm blanking right now, rstrip or something, all these built-in functions or methods that Python compiles into the language itself, you'll see that same type for those. So you see Cython is now giving us the ability to compile something basically into in a lower level way, accessing the, I don't want to say it's compiling into Python itself, but it's creating built-in function or methods for us rather than just regular Python functions or methods. Okay? Yeah. That's correct. Yeah, thanks for mentioning that. So I should mention that this line that we had to do here when we're doing it manually, this is essentially what IPython's doing for us when we use the %% Cython magic. Okay, so that's the big benefit there. Question?
If you supply documentation strings in your original,
It'll show up here. Yes. Mm-hmm. That's right. Question?
do you mind to say it's a Cython function or a built-in function?
Interesting. I've not seen that before. What does it do? Are you using regular Python or IPython? That's correct. Yeah, it will be able to introspect doc strings, but it won't be able to introspect the function signature. You'd have to put that in the doc string manually yourself if you want that to show up. That's right. Okay, so fire by Python, let's just test it out here. Import fib.fib. Call it with no arguments. Gives you what you expect. Fib of string. Tells us an integer is required. Now, this exception is slightly different than the exception you would get if you had the equivalent Python version of this function defined. When you, let's just look at fib here quickly again. So here fib, it takes an integer as an argument. And when you call this function, fib is going to restrict that argument type to something that can be converted into an integer right there. Okay? So you're statically typing n, and you're going to get an exception at that point in your process. So it's if this were a pure Python function, you obviously couldn't type the argument as integer n here. And if you passed into a Python version of fib a string, it would take that string and keep on going with it without any problem. And the only point you would get an error is when you try to multiply that string by a float or do something invalid with that string later on. So you're going to get much further in your Python code than in the Cython code because Cython is now restricting the types of the objects you're working with. Okay. So there's this other way of working with IPython that's also very nice, and called pix import. And what it does is it allows you to import a Cython source file as if it were a pure Python module. And it looks and it detects changes in the Cython file and it recompiles it if necessary. And if it's already compiled this same version of an extension module, it will just load that cached version for you. So it's great for very simple cases. You can't use it for wrapping stuff, unfortunately, but it's great for just doing very simple stuff. So let's give that a try here quick. Actually, in the interest of time, I'm going to show you that in a little exercise that's coming up here in just a little bit. But I should mention at least the syntax you use for it is down here. You import pix import. This comes with Cython. So you have it ready to go. And you would say pix import dot install. So that basically allows pix import to hook into Python's import mechanism. And now when you import something, pix import comes in and says, are you trying to import something that's a PYX file? And if it is, then pix import will intercept that import call, compile it for you into extension module, and then load it in as if it were just a regular .py file. So it's totally transparent now whether you're working with a Cython source file or Python.py file. Question?
So if you have the library file in the same folder, what has preference?
That's a good question. I believe the .py file will have preference. I've never done it before because it would just confuse me, so I've never tried. But so again, this is really nice. Just a couple of lines you can stick in there, and now you can treat a fib.pyx file as if it were a fib.py file, and Cython will be called for you automatically. Okay. There's a bit more work to be done if you're on Windows to basically tell it which compiler to use, but we'll see that in the exercise here. Actually, the next exercise, the sync exercise, we'll see that example. Okay. So a very simple hello world example. Sounds like a number of you have been following along all right, but those of you who haven't, you're welcome to try this one out. So again, inside of the zip file, there is a exercises directory. So go in there, and then there's a hello world directory and a few files here. Okay. Now, there's an IPython notebook. So if your IPython notebook is working, you can just say IPython notebook Cython hello world.ipynb. Fire that up, and you should see this come up. And again, all this is doing is just reiterating what we saw earlier today. So just some description here. We're loading in our Cython magic. Create a very simple add function using Cython. Just takes 2 ints, and it returns some polynomial, those ints. Here's a Python version of the same, pyadd. And then lastly, we are timing it. Okay. Yeah, hopefully it didn't go too fast. Just want to show the, so again, I'm inside of my exercises directory, hello world, and I just ran IPython notebook, Cython hello world.ipynb. Okay. That fired up this IPython notebook, and I'm just now executing these cells one by one. Okay. So Now we're timing to compare the two different versions. The first one's Python, the first one's Cython, add. Second one is Python, PyAdd. And you see it's about factor of 2 faster in this case. So not huge speed up, but they're actually, for this case, most of the work is done just at the calling Python to get to the C. So there's just a lot of wrapper work being done here. Just for kicks, let's just create an empty function. So Cython def no op takes nothing and it does nothing, just to see what the wrapping overhead is for Cython. So the fastest possible function you could ever wrap with Cython, and we're just going to see what the overhead is for calling a do nothing function. So if we do time it now, no op, run, and so more than 50 of those nanoseconds up here is just calling it's just the wrapper stuff. Okay, and if we give it 2 arguments, int A, int B, just to make it a little bit closer to what we had going on earlier. 1, 2. Try that out, see if there's much difference. So there, 120 nanoseconds is just for taking 2 Python integers, extracting the underlying C integer, and calling a do nothing function. Okay, question? Mm-hmm. So let's write a no op in pure Python. No op pi a b pass and time it no op pi 1 2. Give that one a try.
So what's the percent Cython has been executed? Does that mean all the defs that it encounters after that?
Just in that cell. So just in this cell is Cython code. Once you exit this cell now, and you're the next cell down, that's now Python code again. Okay. Excuse me? Yeah. Oh, yeah, sure. Sorry. So the first question was the percent Cython magic. It's limited only to the cell that you're in. The question was, does that turn on Cython for the rest of your IPython notebook? The answer is no to that. It's only in that, limited to that one cell. And then your question was, how do you limit Cython? Just an empty line. Oh, right. Yeah, in the command line. That's right. So if you're interactively using Python in the command line, let me show you briefly back here. You have to give it a complete block of code, and once you exit that block of code, now you're back into regular Python mode. Okay, let me see. So here, let's look up here at our original timing. Okay, so here's our original timing where the functions are actually doing something. Add, the Cython version of add, takes 124 nanoseconds. The Python version of add takes double that. Okay. Now our no-op versions are the same. You see a no-op version of the Cython version takes 120 nanoseconds. So basically, all the time here is being spent just calling, just Python to C conversion. It's just all in the wrapper layer. The actual body of this function is almost for free. Of course, these are very trivial functions. If you're doing anything serious, the body of the function will be doing more work, so this wrapping overhead won't be as much of a hit. Okay. All right, so that's the IPython part of this exercise. And it's a very simple exercise just to make sure people are on the same page. So let's quickly go through the, oops, where am I? Here we go. So quit out of that. Let's look at the the pix import part of this. So let's look at use piximport.py. Again, I'm inside of exercises hello world. So here's use piximport. And here's our piximport boilerplate. It's very simple. Import piximport, and then piximport.install. That's all you have to do. I should say that's all you have to do on Mac and Linux. I apologize I didn't get the Windows version of this in this exercise, but it is in the sync exercise a little bit later on, so just bear with me here to see how to do that. So now we can say import Cython hello world, and that's a pyx file. And now we can just say print Cython hello world.add12, as if it were, again, it just feels now just like a regular Python module. Okay. So here's Python hello world.pix. It's just our add function inside of a pyx file. Okay. So let's try that out. Python use pix import. It runs, and again, it just runs as if it were a regular Python source module. Now what I'm going to do, I'm going to make sure I get rid of any cached versions of this that I may have compiled before. So I'm going to remove this directory. Cython, by default, will stick the piximport build products inside of this .pyx build BLD inside of your home directory. So I'm going to get rid of that whole directory to force piximport to recompile for me. Okay, so take my word for it, it just recompiled and imported the extension module and ran it. Okay. All right, so that's the piximport part of this. Lastly, let's do it all by hand. So we have a setup.py file. So here's our boilerplate. We're importing what we need from distutils and cython.distutils. And we create an extension object here. We give it the name of the extension, Cython hello world, and we give it a list of sources. Here it's just one pyx file. Later on we'll see pulling in more stuff into that. And then we have our boilerplate setup call. Okay. All right, so let's run this. Again, the magic incantation is Python setup.py build ext -- in place, like so. That's on Mac and Linux. Again, on Windows, it's -- compiler equals mingw32. Okay. So get rid of that line because I'm on Mac. So run this, and first thing, again, you'll notice is it's Cythoning Cython hello world to Cython hello world.c, and calling GCC for us to create our object file, and then compiling everything together into our extension module. Okay.
What's the reason doing it that way than just using pyx?
Piximport. There are several. Yeah, you have much more control over using it this way. If you have a larger project where you have several Cython source files, you want to have control over, let's say you want to give someone an extension module, but you don't want them to have Cython installed to use it, then you would use something like this to generate the source code for you, compile it yourself, and then ship it off to them. With piximport, your users have to have Cython installed and just another dependency, that sort of thing. You can be more certain that this version will work because it's using lower level Python stuff, and the piximport version might not work based on your user not having a proper setup. But if it's just for your day-to-day work, for your own research, for just speeding up your own code, definitely go with piximport. That's going to be a lot easier to use. And for interactive work, go with the %% Cython instead of IPython notebook if that's working for you as well. Okay. Is there another question? Yeah. It does, but distutils comes with Python, so that's built in. That's ready to go. You know, that's a good question. I'm pretty sure it does. No, you don't need to write this at all. It's essentially generating that file for you and doing all that for you. The only thing you need is just import piximport and piximport.install. That's it. All right. So that was our first exercise. Again, just very, very basic, just to make sure we flush out some of the basic ways of working with Cython. Okay, we'll see more interesting exercises here in just a little bit. Okay, so let's go a little bit more formally now as far as what's going on. How do we declare C stuff using Cython? Well, typically what you do is you just tell Cython, I'm declaring something as C, so I use cdef. Okay, and cdef is a new keyword it's a new Cython keyword, and the way you use it again is if you want to declare local variables, you just say cdef, and then you declare after cdef as if it were a C variable. Okay, leaving off the semicolon, of course.
What kind of limit is, of the sizes that you use?
It's going to be just as if you declare this as an int in C.
So it's different from Python, where
Correct. That's right. CPython and int, a CPython int is a C long, whereas this is a true C integer here. If you wanted a long here, you could say cdef long, and that would be a C long. Okay. So yeah, this is not a Python int at all. This is definitely a C int. Okay. Whenever you see cdef anywhere, you are making a C declaration. Okay. So you're working with C level things. Okay. If you want, you can create. I should mention that this function fib is a Python function generated by Cython, okay? So it can be called from Python. It acts just like any regular Python function. That's because it's a regular def function. If you want, you can create a C function in Cython using cdef instead of def for the function declaration. So here we're saying cdef distance, and we give it a return type float here. And all this is doing is taking two C arrays, pointers to C arrays with a length n, and it's just, inside of the body here, it's just getting the distance between these two C vectors, okay? And the way you should think about this is when you create a cdef function like this, you're writing C with a Python-like syntax, okay? You're no longer writing Python code anymore. This thing that you're creating, this distance function, is a C function. It's not a Python function anymore, and it's not available to call from Python. It's declared static inside of your C source file that's generated. So it's only visible to other things inside of that source file. Okay, if anyone you know anything about the static keyword in C. And there are reasons for that, but the important thing is that you're writing a C function using Python-like syntax. So the name of this function is distance. It returns a float, and it takes a pointer to a float as x, pointer to a float as y, and then an integer n. Okay, and of course, there would be no way. There's no Python analog to a C pointer, right? So you wouldn't, even if there was some magical way to make this callable from Python, it would not be obvious at all how to make this work out of the box with Python, with that function signature. Yeah.
Can you make the function return void and by reference to y? Can you do that? Or do you always have to return something as a function?
You can absolutely say cdef void and have a void function. That's perfectly fine. Yeah, whatever you can do in C, you can do here. It's just got a little, it's kind of like a Python-like syntax for declaring a C function. Okay. We'll see in a little bit how to do structs and unions and that kind of thing. Question?
So if the cdef float distance is not reachable within Python, it's just a helper function for my Cython code?
Correct. Yeah, we'll see in a little bit a way around that. Okay, using another keyword. We just want to get through cdef here in a little bit. So the function arguments are a float pointer, and an integer. Those are also C declarations. You don't stick cdef in front of those, though. Okay, so it's the one place you don't use cdef for declaring a C-level thing. Now, here's another way of using cdef inside of this function. We do cdef colon, and then inside of an indented block, we have all of our declarations as if they're in C. That's equivalent to doing two separate lines, cdef int I, and then cdef float d equals 0.0. Okay, so those two options are equivalent. When I have a big block of C declarations, I kind of prefer to do that just because it groups things a little bit more nicely. Okay, but they're equivalent. Lastly, down here, I just want to put it in here for completeness. We'll talk about it in more detail later. We're declaring an extension type here with a cdef class particle. Okay, and we'll go into all the details of extension types in a little bit. But inside of these extension types, you can declare things at the class level as cdefs, and that has particular meaning as well. Okay, and again, we'll go into that later. I just want to have on one slide all the places you would use the cdef keyword. Okay. You know, Cython can generate C99. I mean, it'll generate C code, and I think it supports C99 features as well. I have not tried it yet, so I'd have to look into that, but I would see no reason why it doesn't. I know it supports like C99 complex variables and that sort of thing, so it'd be worth looking into. Okay, so here are three versions of a distance function using def, cdef, and this new keyword now, cpdef. We'll see what that is in a bit. So the first version here is just pure Python, and this is also valid Cython. Okay, so Cython is a superset of Python. Anything that's valid Python is valid Cython as well. Okay, so this is Python or Cython. If it's in a Cython extension module, you can just call it from an external Python module somewhere. Okay, so this is available to the Python level. This is our cdef float distance. Again, this is not available to external Python code. This is only available to Cython code inside of this source file or inside of the IPython cell that you happen to be defining this in. Down here is a cpdef function. And cpdef is a new Cython keyword, and it's designed to essentially get around this limitation that cdef functions are only visible inside of the source file that you defined it in. So cpdef, what it does is it actually creates two functions. One is a C function only, and if other Cython code calls that function, it will call the C function, and then it creates a very thin Python wrapper around that C function. And that makes that C function available to the Python level. Okay, so it's creating two functions for you, a C version of this function and a Python version of this function. But cpdefs are somewhat limited in that you have to give arguments and return types that can be converted to and from Python types. Okay, so our distance function here that took two C array pointers, you couldn't take that and just declare it as cpdef. That wouldn't be allowed because, again, Cython doesn't know how to take something and convert it to a C array out of the box. Okay.
How new is CPD?
It's been around for a while now. I'm not as long as I've been using it, which is 5 years or so, 4 or 5 years at least, I'd say. The question was how new is cpdef? It's been around for a number of versions of Cython. So what I had to do is I had to take my C array pointers here and convert them into typed memory views. Okay, so this is a little teaser for the later part of this course here. So what are typed memory views? Well, we'll see how to use those and what they allow you to do later on. But this now essentially gives us the ability to work with NumPy arrays or buffers of memory, that sort of thing. And it's compatible with Python, so it'll work. Okay. All right, so def functions available within Cython and Python, but they have Python overhead, so they're a little slower. cdef functions are just pure C things, so there's almost no overhead. They're going to be very fast, but the restriction is that they're only available within that source code. And lastly, cpdef functions create two functions for you, a Python layer around a C core. Okay, Cython will call the core, the C core. External Python code will call the Python wrapper for you, so you get the best of both. All right. So here are some examples of using these def and cdef functions. I'm not going to go through this in great detail in the interest of time. but just suffice it to say we have a function here that's calling a smaller function inc. And here inc is a def, so you can call inc outside of this Cython source file inside of our Python interpreter here, and it works. Over here, we've created fastinc, and it's a cdef function. So it's now available only within this PYX file. So fastinc seq can call it, but you cannot call fastinc outside of the PYX file. Okay, and then here's a version using cpdef, and just illustrating that you can use fastinc outside of this source file as well as inside. Okay.
Does that slow down the call to fastinc?
There will be no slowdown when calling it from Cython, because it's going to call the C version of that function. It will be slower from the Python layer, because if you call it from the Python interpreter, it's going to have to go through the Python layer to do that.
But the alternative would be to call a function inside that module that calls
Right.
the fastinc, which probably would be slow.
Still, it's going to be slow. Yeah, whenever you're calling from. So the question is the speed implications of calling this. It's going to be fast inside of Cython, and the only way to get to it from Python is to go through the Python layer, and that's going to have to do all those type conversions, and there's going to be Python overhead no matter what you do there. Okay. Yes, we'll see that in a little bit. Good question. Yes, all three are allowed in classes. We'll see that as well.
So cdef had an actual Python file called whatever the function is or whatever, and then you have this binary
Mhm.
associated with it. Right? Is it kind of like Swig? It sounds like it's a lot like
No. cpdef doesn't. To you, it's totally transparent. You just define one function. You just pretend it's just one function. And Cython takes care of whether it's being called from Python or from other Cython code, and it calls the right version for you. But you don't worry about that at all. Okay.
Why not just always use cpdef? Does it just clutter your namespace?
So question is, why not just always use cpdef? And the answer is, sometimes if you have let's say you have a function like this that takes pointers as arguments, right? Pointers are everywhere in C, but there are no pointers in Python, like true C pointers in Python, right? So you could not declare this as a cpdef. That would not be allowed. Okay. cdef functions, you have access to all of C, but you can't call them from Python. cpdef, you have to make sure that the argument signature is compatible with being called from Python. So they're more limited in that respect. Question?
Can you show us an example of processing NUI arrays?
Yes, that's the capstone exercise. Absolutely.
So if you are declaring them like this, do you not lose the whole optimization benefits of the registers and CPU?
So the question is, declaring cpdef functions, do you lose optimization of just C-level stuff rather than?
It sounded like you were saying earlier that the basically optimization comes through the types of seeing that versus a register.
Yeah, well, in the body of this function, you're still able to use as much C as you like. So the body of the function is perfectly, you can unpack stuff and use C pointers inside of the body. That's perfectly fine. It's just the function signature that has to be compatible with Python. That's the only restriction to cpdef functions. Okay, so just very briefly talking about C import now, another Cython keyword. There aren't too many. We're through almost all of them, I think. And what C import allows us to do, at least one thing it allows us to do, is pull in stuff from other C header files that are wrapped for us with Cython. Okay, we'll see it in more detail later on, but I just want to talk about this one part of C import for the next exercise. So here I'm importing stuff from Python in these first two lines here. So from math import sign is PySign. So again, this is familiar to all of you here. You're using just the sign function inside of the Python math file. And this is a Python function that's got a Python layer on top of it. And it's wrapping the math.h sign underneath for you. Okay. There's also a NumPy universal function that lives inside of the NumPy namespace. So you can say from NumPy import sign as np sign, for example. And this is a universal function that's calling sign underneath the covers as well, and it works with Python scalars and with NumPy arrays, right? You know all about that. So now here, let's say we want to access the sign function from the C standard libraries math.h. Well, you can do that in Cython, because Cython ships with wrappers for all these standard C and C++ headers. And we can say from libc.math, C import sign. Okay? And if you want to import malloc and free from standard libc.standardlib, you can say from libc.standardlib, C import malloc and free. So again, this only can go inside of Cython code. This is not valid Python, obviously. But this sign here that we imported, C imported from libc.math, gives us access to this C function, sign. So there's no Python overhead when calling this sign function here. You can, of course, do this in Cython. You can say from math import sign as PySign and call it that way. But when you call PySign at the top here inside of Cython code, you're going through the Python layer. So you have to convert, let's say you're calling PySign with a C integer as an argument, or C float, let's say. It has to convert that C float into a Python float, give it to